So what we're going to do is we're going to explore a little optical system that's going to show us how this works. And so this is a hole in a piece of paper, and it's called a pinhole. And it is a part of any optical system out there. And so your eyes, right, have a hole, it's called a pupil. Cameras have a hole, it's called an aperture. A telescope has a hole, right? Not the hole that you put your eye up to, but the other end where the light comes in. So this is a really important part of any optical system. And so we're gonna explore this. And so in my investigation, I'm saying that this is a whiteboard that really is projecting all these images on the screen. And so to help us really see how that works, we're going to dim the lights, and I'm just going to use a blue and a red light to see if we can illustrate what I'm talking about, how this works. So let me make it a little bit different here. Ta-da! So now what do we see? Is my whiteboard still white? You're seeing dots, sorry. Yeah. There's going to be lights going on in here. So, but yeah, what is my whiteboard now? Is it white? Purple. Okay. So now I'm going to make another claim, and I'm going to say what you're really seeing is no longer are you seeing a white screen, and you see hues of blue and red and purple, making purple. But really what you're seeing on this screen is billions and billions of a red light and a blue light. And you're like, what? So we're gonna use a fancy little device to show you how this works. And so if you would humor me, and inside your little tube, you have an index card. I think they already punched a hole in them. They weren't supposed to. And so what we can do is we can use a pinhole to isolate all the images that are being projected on the screen to just one or two images. And so if I hold my pinhole up behind this light, I can see, I don't know if anybody's able to see behind there. Can you guys see behind there? What do you guys see? Red and blue. Yeah. And so if you hold your pinhole up and you need a screen to project it on, or if you hold your pinhole up, and so you'll need a screen behind your pinhole, so if you have maybe a piece of paper that you can hold behind your pinhole, or a screen, and you gotta get it just right because this is tiny stuff. Are you able to eliminate all the objects in the room except for a red light and a blue light? And so the way that works out here is, and you might, it's better to sit closer. So you need your pinhole first, and the pinhole needs to let light through it onto a screen. And so the closer you are, the easier it is to get it, but how many of you are having success with that? Some of these folks say, yeah, awesome. So yeah, let's explore this cool, tiny little hole in a piece of paper called a pinhole, and do some investigation on how this works. So if you will do me a favor and dump out all your supplies, be careful because there's a push pin in there, and don't lose it, and don't stab your finger with it. I'll just put these up just a little bit so we can see. But we're going to build our own pinholes and start some investigations. So how many of you guys are getting a red and a blue light in your pinhole? Awesome. So, but there's something really interesting that's happened though. What's happened to your lights? So I'm going to move these around and you tell me what you notice. So hold your pinholes up and I'm going to raise the lights up. They're dropping. Uh-oh. Okay. Now, oh, the other way. You want the wax paper? Yes. And the tin foil should be towards the light. Do you have a little hole poked in your tin foil? Okay, perfect. Now I'm going to lower the lights. I'm lowering the lights.
No.
What is happening?
No, it's your raising the lights.
All right. So now I'm going to move them to your left. I'm moving the lights to your left. Which way did they go?
Right.
Okay, I'm going to move them to the right. Which way did they go?
Left.
What's happening there? So our images now become inverted and reversed. Huh. So let's continue to explore how this works and what is making this happen. And so let's just start with one light. So we have our red light. And so when we have one light, how many images do we get on our screen? One. Okay, so what do you think will happen if I poke another hole in my tinfoil? How many images do you think? You think two? Some people are predicting two. Shall we try it? So poke another hole in your tinfoil. So here's where you can have your students think about a mathematical equation. What mathematical equation? That's what we're going to work towards. So we're going to be investigating and exploring the number of holes versus the number of light bulbs. Can we figure out how many images will be projected on our screen? All right, so we had one hole, one light, we got one image. I've got one light, two holes, how many images? Two images. So let's poke one more hole, you think? Before we add another light? And so I have three holes, one light, how many images? Three, okay. Anybody want to make a prediction of how many images we'll see if I add another light? So yeah, so we have, how many holes? Three holes, two lights, and we saw 6 images. So is anybody being able to figure out what's our mathematical equation where we could predict the number of images? Huh? It doubles? Do you guys agree with them?
Image equals.
So let's try that. Let's do an easy number. We have 3 holes. Let's poke in 2. That'll make it 5. And we have 2 lights. So then how many images should we see?
The number of holes times the number of lights equals
The number of images.
Okay, so then how many should we see then? If we have 5 holes, we're going to put, okay, let's test it. Let's see if that theory is right. I can't see where I poked holes before now.
So we should have 5.
Yeah, so you should have 5 holes in your tinfoil. We've got 2 lights. And so what do you think? Do we see 10?
Yep.
Yeah, nice. Okay, so now we have some math in there. Good job. Has anybody noticed what's happening? So as we do these explorations, I really want you to pay attention to the individual lights. What is happening to the brightness and the sharpness of your images on your screen as we add more holes in? So have you guys seen a notice? Have you seen a difference between when we punched our first hole till now?
It's increased.
What's that?
It's increased.
What's increased?
The
light?
brightness.
The brightness? Okay, the brightness is increased. Okay, is our image, what would you say? Is it still sharp?
That's it.
So. Well, let's, what happens if we poke a couple more holes in here? Let's poke a couple more holes and see what happens to our image. But yeah, so has anybody poked a bunch of holes in that have overlapped yet? Some of yours are starting to overlap. Anybody else have images that are starting to overlap now? Not yet. Okay. What are you noticing with your overlapping?
The ones that are closer together.
Trying to combine back into a nice shade of purple.
A light shade of purple where those colors are overlapping. I'm gonna add a green.
Almost like a kaleidoscope.
Yeah. Let's see what happens when we put a green in there.
Ooh.
Yeah, I heard that, yes.
Now there's a lot more overlap.
There's a lot more overlap. So when mine are pretty bright. Are your lights pretty bright still? Mine are pretty bright still. My lights are not as clear as when we started. Do you guys agree with that statement?
The holes are closer together. They become blurred, but if you have one that's further out, it's still
Clear. So let's poke about a couple, 4 or 5 more holes in there. So has anybody else got some color mixing going on because your holes have overlapped. Yeah, depending on the rotation. Nice. So where the green, the blue, and the red meet, what color are you getting?
They got purple, yellow.
Should be getting white.
Yes.
Mine aren't overlapping, but it should be.
Yeah, you're right though, yeah. You should get to a place where eventually all those colors overlap and you're getting white again.
I've done this with my kids with lenses on flashlights,
Oh,
and they merge the lights, and
Oh.
when it hits white, they freak out.
perfect.
They're like,
Yeah,
alright, now we're gonna do less.
we have extra supplies at these front tables up here, okay? And so you're just building a pinhole, so you're putting wax paper on with a rubber band on one side, tin foil with a rubber band on the other side. All right, so let's keep poking holes. And again, I want you to pay attention to the sharpness and brightness of the images. Okay, so quickly, so what are we noticing with the more holes we're adding? What's happening to our images? What's happening to the brightness? What's happening to the sharpness of those images? Have you guys noticed anything yet?
More bright, less sharp.
Okay, would you guys agree with his statement? It's more bright, but it's less sharp.
Yeah,
Okay,
I agree with that.
all right. I thought of something. I lost my brain. Okay. So here's the problem then. If we're looking at objects, astronomical objects in the sky, right? And we're talking about the night sky right now. If you're looking at these objects and they're dim, right? You need a bigger hole then to make them brighter? Is that what you're saying?
More yet than magnifier.
We're not there yet. We're just with a hole. We're just with a hole. So, right? So he's basically saying the more light you're letting in, that image is not as sharp and crisp as it was when we first started, right? So smaller holes better, but then that's really dim. So maybe then we need one large hole. Do you think that would work? Let's try that.
Why not just a longer exposure?
Longer exposure. So let's take a fresh piece of tin foil and let's try making one large hole. So I forgot to finish going back to this. Remember we were lifting up the light and you said it was going down? And then I was lifting it to the left and you said it was going right? I have in your supplies foam with skewers. Another, they're probably like another device that I cannot give my students, right? But you can model with your students what's happening. So let me take this one out first before we add the green. Let's talk about, because now we can start talking about properties of light. So if I put a skewer into my phone, and somebody gave me skewers that don't have it. Here we go. So this is my skewer modeling these lights up here. So I've got a blue light and I've got a red light. And so remember we saw that the image was inverted and reversed. So you can have your students model what's happening with the light. Where's my pinhole? So here's my pinhole, and the light comes into, so does that is a great model of why the lights are inverted, reversed, because light travels in a straight line. And so when it goes through the pinhole, there is your red light and blue light, and when they go through the pinhole, they cross, because light travels in a straight line. So now I'm going to add the green light, and what do we see? What's the order of the lights? So we got blue in the middle, and the red and the green are on the opposite. So if you use your skewers and your phone, how do you explain why the blue's in the middle and it's only the red and the green that switch? What can you show with your skewers in your phone through your pinhole?
But the middle's circle.
Yeah,
The middle's going straight through.
yeah, the middle's going straight through, and so, where's my middle?
Yeah.
Kind of, yeah, So, but yeah,
So that these two go like this.
yes,
but that one
and the middle goes straight through, perfect, nice. Okay, I lost it, there it is.
Pictures are back.
Alright, so we have our one little hole, and we're looking at that image, and it's pretty dim to me. It's pretty dim, but the images are sharp, I can make out the light bulbs. So we're gonna see what happens when we make, instead of a bunch of little holes, we make one big hole. So let's take our push pin and make it the size of like a thumb. What happens if we make, is that too big? Try smaller then if you want, yeah. Ooh,
fuzzy.
fuzzy,
Yeah, fuzzy.
I
Yeah.
got fuzzy.
but pretty bright, right?
Yes, brighter, more overlap too.
More overlap, yeah.
And the shape of the hole.
That's so cool, it's so pretty. So this could be an art project, like we said, art project, you could do a mathematical equation with this.
More big holes.
You can discuss properties of light.
Yeah. That would make it difficult.
Alright, so this is the problem, and you already hinted to it earlier, was this is what astronomers go through, right? You're looking at these dim objects, so I need a big hole, because I gotta let a lot of light in, but then my image is not sharp. So here's the conundrum, how do you fix that? If I have a small hole, I get sharp objects, but they're too dim for me to see. So what do we need to do then to assist us in making, having a large hole, so you let a lot of light in, but crisping up that image? Lenses. So think about, we're talking about an optical system, right? Your eyes, cameras, telescopes. So we have our hole, the pupil, we have our lens where the image is projected on. So now we need a lens, and that's where a lens comes into place to now, not magnify, but sharpen up that image. So you guys have some lenses here. You guys can grab those lens holders, because I didn't have enough. But you can test the lenses. Which lens are we gonna use? We have a couple different lenses. So you have your pinhole, you can use this white paper as a screen if you need to, and see, where do you then put that lens? Where does that go in the order? So that's something you can explore. Do you put it before the pinhole, after the pinhole? Where does that lens go? So to sharpen up that image. So how is that looking?
You can see everything, just to put out.
So you gotta figure out where to put that lens. Oh, look how that your image sharpened up immediately.
Turns from blurry to, sharp all
This is no longer just the light.
I think that's sharper than the original.
So we had a couple different lenses here, so did anybody try the other lens? What happens? It looks like everybody went to the convex lens. What's happening with the concave lens?
Ooh, that's some images.
And how can you model that with your skewers? Convex, it has the bigger middle. If it dips in, that's concave.
It's just the same thing that's happening with corrective lenses, like
Yeah.
glasses,
Yeah,
pretty much.
exactly.
Ooh, we got towards the edge.
So try both lenses and see which works better. You have a concave and you have a convex. So which is going to fine tune that image for you? Which lens do you need? I think it's the angle that you're at. You need to be more where you can see the lights individually because they're kind of blended into a row. Yeah, you need to sit more where you can see the individual lights. Sorry, yeah, that's just your position. So you can pop back, like sit at that back table maybe, where that lady is or something. So which lens do we want to use? You guys explored both.
Well, it depends on what you're trying to do. you're gonna want the convex lens for a sharper image, but if you're going to light, you're gonna want the concave.
Yeah, so can you guys model what's happening? So this took me a minute to wrap my brain around. So you have to imagine that this is the bottom of the lens. So if I have the concave lens, which is the concave? Yeah, it dips in, right? And so how can you demonstrate to your students what's happening to the light? Because the concave spreads the light out, right? Yeah, so this is what's tricky because I want to look at this, so this is what's happening to your light. And so I see this bump here, this bubble, so to me that I think of a convex. But you have to tell them to pay attention to the bottom. This is the bottom of your concave lens, okay? And so your convex lens, right, it bubbles out, and so it narrows the light in. So this is using sticks and foam is a great way to illustrate to students the light path that the light is traveling and how the lenses are working, focusing the light or spreading out the light, if that makes sense.
Both of them, so I put this one right here.
Holy cow, we ran through this. So the next thing that you could do with your students is find the focal length. Does anybody know, how do you find the focal length of your lenses? So that would be a great, if you're looking to enrich the students and do some math, so you could figure out the focal length, give them different lenses. And so the focal length is between where the lens is to where the screen, the image is projected on a screen. That will give you the focal length. So they can get out some meter sticks or rulers or something and start measuring because they want to see where that image is perfect, where it projects it perfectly clear, and that would give you Yes. Yes. Yeah. So then, wanted me to just talk a little bit about the observatory and what we do up there. So we are open to the public. So I always tell New Mexicans you should be proud of your state because if you've never been to Sunspot, New Mexico, we are our own zip code. So we're a little village, but you have 2 observatories there run by New Mexico State University. You've got Sunspot Solar Observatory where we're studying the day star, and then you have Apache Point Observatory and they're doing the night sky. Unfortunately, they're strictly research and they're not open to the public, but Sunspot is. And so we have a museum, we have gift shop restrooms, we give tours of our telescope, there's a walking path that you can walk around. So our site is relatively old. We were founded in 1947. And so you're gonna see that in some of our buildings, the neglect, because we only have 1 actively used telescope. All those other telescopes have either been, they're obsolete and outdated, or really it's expensive to run an observatory, and the university is really only concentrating their efforts on that 1 telescope. But yeah, if students come up on a field trip, we get tours of the observation room, the icing on the cake. If they're actively observing, you're gonna get an image on the monitors, because we're looking at the sun, and we're looking at it in multiple wavelengths, just not the visible. We're looking at in infrared and ultraviolet. It's not safe to have an eyepiece on the telescope, and so everything's fed through our monitors. Look at that light image, and then we do hands-on activities with kids. So we have a few lessons that we offer to schools that they come. We can do hands-on activities. But I appreciate you guys attending, and I hope that you picked up some stuff that you can take back to your classroom.